All right, well, thanks, guys. Hi, I'm Tommy. I've been studying topic models since about 2013. Topic models and their newer cousins, text embeddings, are latent variable models of language. Latent means that you don't see what your model is trying to estimate, and that makes it hard to know whether you have a good model or a really, really bad model that just looks good, or a really, really bad model that you don't know if it's good or bad or not. And I am, among other things, a PhD student, and my research centers around ways to make topic models better. In that vein today, I'm going to talk to you about a little experiment I ran. So before we get to that, let's take a step back and just review things. So first of all, a quick show of hands. Who here has heard of latent Dirichlet allocation? And it's a good number of people. Who here's used it? So that's probably about a third of the room, actually. So that's pretty good. So LDA is basically probabilistic matrix decomposition. You have three hyperparameters. So K is the number of topics. You have to fix that yourself. Alpha controls the concentration of topics within a document, or what's in that theta matrix there. And then beta controls the concentration of words within a topic, or that phi matrix. And anyone who's used LDA or talked to somebody who's used it will probably find somebody who is freaking out about what do I pick for these things, especially that number of topics. I have no idea what a right or wrong answer is. And a little note on vocabulary, since I know it's in our conference, there's lots of statisticians here. So in machine learning land, they use hyperparameters. The definition is slightly different than Bayesian statistics. So in machine learning land, a hyperparameter is anything that you have to set as a modeler rather than a parameter that is learned or fit while you're training this algorithm. So that's how we're using that today. And so the foil for my LDA in this comparison of this experiment is latent semantic analysis, or LSA, or LSI. Quick show of hands, who here has heard or used this method before? Actually, fewer people than LDA. That's actually kind of crazy. So LSI has been around since about 1989. So it's not probabilistic. It's just a matrix partitioning algorithm. So you take a document term matrix or a TF-IDF matrix, and you are going to factor it using a single value decomposition. It's not, what you get isn't probabilities, but in general, you're still getting a distribution of topics amongst a document and a distribution of words within topics. It really only has one hyperparameter, and that's K, the number of topics. You could get fancier with this, but for now, the simplest version, it's just that one. And like I said, topic models and embeddings, they're latent variable models. They're hard to evaluate. The overwhelmingly most popular evaluation method is something called semantic coherence. So there's a bunch of different measures for this and formulas, but the idea here is that you can look at a distribution of words from a topic, and as a human being, you're like, oh, that makes sense to me. And so the one that I use often ships with TextMiner. It's a package I wrote. That tries to look at the probability of words co-occurring within a document controlled for statistical independence of those words. Don't worry about that now. So coherence is a really popular way to evaluate these models. I'm not going to talk about goodness of fit. I can bend your ear about it later in the break. And then task-specific accuracy. So a lot of times people are not using topic models or embeddings because they actually care about the model itself and want to interpret it. Instead, what they're doing is trying to make some sort of numeric features of text and then feed that into some downstream task, like document classification. So maybe we can say a topic model is good or not good if, depending on how well it does on this downstream task. So the two things to keep in mind as we go forward and I tell you about this experiment is coherence, that's sort of like how interpretable is this. Accuracy, that's sort of like how well did this do for whatever that downstream machine learning task was. So I've actually been introduced as, this is Tommy. He still uses LDA, but other than that, he's okay. A whole chapter of my dissertation is just going to be this GIF on repeat. Last year especially has seen an explosion of deep learning-based text embeddings that have really advanced the state of the art in natural language processing. But here is my argument for why this still matters. So first of all, people still use this model like a lot. So knowing how to do it better is very helpful to a large number of people, even if we're not state of the art. Second of all, I think that studying these comparatively mechanically simpler topic models can actually give us some insight into these much fancier, more complicated deep learning embedding models that are arguably trying to do largely the same thing. And third, we stopped, like the machine learning community really stopped studying LDA when deep learning for image recognition came out. And so we never actually even really learned how to fit a good LDA model before we stopped caring and moved on. So I'm actually not convinced that a well-specified LDA model wouldn't be fairly competitive with some of these newer methods. But watch this space in the next couple of years and see if I try and write that paper. We'll see how right or wrong I am there. That's what my gut's telling me. But if you insist, so in this work, I used a neural network to write R code to use a Bayesian optimization service for topic modeling. So I've already really spoken to this a bunch today, but topic models are hard to evaluate, but think about what people use them for. That's either I want to interpret something from it, or maybe there's just this downstream task that's a little bit more objective than this fuzzy latent variable thing. And so maybe we can optimize a topic model for these things and see what the mechanics were that led to doing well or poorly on that task. Right, so here's basically the goal. Take a topic model, use it to embed some documents in some latent topic space, use that embedded text to train a classifier. So for this, I used the 20 news groups data set. And if I can date myself just a little bit for the younger folks in the audience, a news group is like a subreddit, but from the 1990s. And so the task here is to predict from which of these 20 news groups or subreddits the document came from. And so the idea here is that using my optimization service that I'm going to talk about in a little bit, I'm going to create a bunch of observations around what hyperparameter settings gave me what values on these evaluation metrics, so I can get a sense of what are the underlying mechanics of these models and how do they work. This is an R conference, so I don't have a ton of R code. That's just not my style, but here's my tech stack here. I have a policy against reading slides, so instead let me justify the selection of random forest. Again, neural networks are eating the world. Random forest just works. It's like an 85% solution. And since I wanted to spend my time studying the topic models, I didn't want to pollute that with a more complicated model that has its own hyperparameters that need to be tuned and optimized. I wanted something I could just use out of the box. So I just straight up used the defaults from the random forest package. So I've talked around this a little bit. So I used a hyperparameter optimization service called SigOpt. What this is it's an ensemble of Bayesian optimizers. So every time you report an observation of, with these hyperparameter settings, I got this evaluation metric score, it says, well, then try these new ones. And you're basically creating a data set on how well your model searches through this space. Ideally, you're fitting fewer models than using random search or grid search, so you can get to something optimal quicker, but you can also still create this data set of how well my model performed and study it. So basically, you take your training data, you train a model, you report this to the service, it then suggests new hyperparameter settings, you wash, rinse, and repeat, do that in a loop, and then finally you get what might be an optimal model according to that metric you're trying to maximize. Full disclosure, my company has invested in SigOpt, so I'm not just a client, I'm also an investor. But I've used it here, I've used it for my deep learning class, which is the last class of my PhD, which I did last year. So investment status aside, I think it's a pretty nifty tool. It's pretty useful. It's helped me. So at a high level, this is the process. Take your documents, clean them, then you're going to train a topic model, then you're going to train a classifier, and stick this SigOpt optimization loop in the middle here. Pretty standard cleaning and curation process. I used unigrams. I removed both stop words and words that appeared in fewer than 5 documents. Nothing crazy there. But because of the scalability issues of LDA, or at least the Gibbs sampler that I wrote, and using SigOpt, I ended up with some pretty wonky training and test splits. So I split the data set into thirds at first. So you have your training set, then you have your validation set, and then finally you have this test set. And instead, I took my training set and then split off the first 1,000 observations, used that to train the topic model, then got topic predictions for the remaining 5,600 observations, used that to train random forest, and then for that middle validation set there, I then got topic predictions and then random forest class predictions, and then reported those metrics off to SigOpt, so that was all out of sample. I haven't gotten to that bottom set here. This is an ongoing work for a blog post I'm writing, but what I'll do for that last one is just take whatever optimal model I choose and get a true out of sample thing. So then here, this is that whole optimization loop. So SigOpt has an R API. It's called SigOptR. It's pretty standard if anyone's used cloud services before. You get an API token. You're going to set it as a system environmental variable. You're going to declare an experiment and hand that off to that API so that it actually knows what the heck it's doing. You're going to declare a function to train your model and calculate those evaluation metrics and report them out. And then you're going to loop over that process that I described before. And so here's the only R code in this presentation. So up there at the top is setting that environmental variable. You don't get to see my SigOpt API key because I don't want that in the public domain. Set this experiment here. So I've got K, I've got alpha. Ask me in the break why that says beta sum, not beta, and then you'll regret asking me that. But I won't let you escape. I will make you learn. And then I ran 4 parallel workers and got 100 observations. So I got a small data set of 100 observations of this hyperparameter space for these models. This big old function does that train test split that I talked about, trains a topic model, applies it to a held out set. Trains random forest, applies that to a held out set, calculates the metrics, and then spits those out at the bottom of the function. And then here in step 4 is that main optimization loop. So there's this system sleep up there. What I discovered is that when I was running it in parallel, my computer got ahead of SigOpt server, and then it would just hang and I would never get any results. So I found that by putting the system to sleep, it would, like, SigOpt server could spin its workers up. I've reported that to the SigOpt guys, like, hey, maybe you should document that or fix it. Their engineers are on the case. And then the bottom's where you get the optimal experiment. So that's all fine in theory. How did this work out for me in practice? So far, so good. Let's use Google instead of my wussy little MacBook to run this. Don't let your code run for a week without checking on it. I can think of better ways to spend $40. I should have seen this coming. This wasn't a huge data set. I don't know what I was thinking. But eventually I fixed it and got results in a few hours. And now I have this nice little issue that I'm going to open up on GitHub that says, go fix your Gibbs sampler. So as I said, I optimized for both accuracy and coherence. And what this plots here is how you get accuracy versus coherence for a whole bunch of hyperparameter settings for both LSA on the left here in purple and LDA in green on the right. The orange lines are what's called a Pareto Frontier. So basically what that's saying is at that point, you can't do better on one of these metrics without doing worse on the other. So these would be considered like optimal points, and then you have to decide, do I care more about interpretability or do I care more about classification accuracy? So a couple things jump out to me right away. So one, LDA, just across the board, way more accurate at that classification task than LSA. LSA only produces more coherent topics for like terrible accuracy scores. So you can interpret it, but the model doesn't seem to be very good at predicting the class accuracy, at least not on this data set. The trade-off between coherence and accuracy for LDA on that Pareto curve is really tight. So I don't have to give up too much in interpretability to get some pretty good prediction accuracy. And then all those points inside of the Pareto curve would be inefficient points, right? And so another thing that jumps out at me is that I think because LDA has a much more complicated hyperparameter settings that you can do, you get a lot more inefficient points, which goes back to my earlier thing of we got distracted before we even knew how to use these models. You know, there's a lot of ways to specify not very useful LDA models, but done well, you can get something that's reasonably good, at least on this data set for this task. So SigOpt, they've got a fancy user interface that I'm not going to bring up now, but they report hyperparameter importance scores. That's sort of like variable importance from random forest or something like that. And so what I can see for LDA at least is that K is by far the most important parameter, so the number of topics is by far the most important in terms of your accuracy. But then all three of those parameters have to work in concert together to get interpretable models, to get reasonably good coherence scores. Again, fitting to this, this is a complicated space. You can fit a model that isn't very good pretty easily. For the sake of brevity, I'm not going to show you all the graphs I made, but in terms of number of topics, here's comparing LDA and LSA. So again, we see in terms of both coherence and accuracy, LDA is a lot better. But another thing I see is that accuracy is pretty high and I get pretty tight groupings across this whole range of the number of topics for LDA. But coherence is a whole lot noisier. Again, fitting to like owning to this, like getting all three of those parameters right when you fit your model is what's going to get you a good one or a bad one. All right, so what? So I guess if you can afford the compute, I would say use LDA, not LSA. I can't really speak to how it performs against these neural network-based methods, but you know, someday I'll test that out. LDA is pretty computationally intensive, but trying to fix my Gibbs sampler has led me to realize that there's been some new algorithms in the last few years where people have tried to fit LDA in a much more scalable way. So let's watch this space. Maybe I'll implement one in TextMiner. Maybe I'll get distracted. Who knows? I have ADD. But one thing to consider here is that I got 93% accuracy on this classification task on this data set with LDA pretty much for free, right? Like out of the box, no matter what my setting of K was, like it was just really high on only 1,000 documents. And then I had held out sets of about, it was about 10,000 or more of the documents there that it ended up predicting on. That's pretty good for such a small sample to generalize that well. Maybe a property of the data, maybe a property of the algorithm, probably an interaction between the two. And so, like I said, I use SigOpt in my deep learning class. I've used it for this product. My company invested in it, but it's a pretty useful tool. I'm also still bullish on LDA, even in 2019. Come find me in the break and I'll talk your ear off and again make you regret ever having asked me any of these questions. And since I've got about a minute left, I want to do a quick pitch. So we're hiring here at In-Q-Tel. I've been there about 2.5 years. I'd reached a point in my career as a data scientist where I'd gotten up into management, and I realized that, management, but I was still writing code for half my day. But I realized that none of my problems were technical. They were all human problems. So like convincing my clients that the data that they had was insufficient for the question they wanted to ask, and convincing them to go collect a sample, and then they would argue with me, no, machine learning is supposed to fix it. And I just was not equipped to win that argument without pissing people off. And so you just end up sort of being like, I guess I'll muddle through and build you a model. So I came to this investment firm, which is a very person-driven business, to specifically work on those skills. And at first I got my butt kicked and had to have my colleagues bail me out of my first negotiation. But bit by bit, I got better and better and better. And more recently, I just had a project where I was able to convince our customers, no, you need to focus on the data. You can't just take this black box machine learning model and get what you want out of it. So I feel, taking a couple years out of direct, doing tech has helped me. So when I go back into the world, I can get the projects that are the right ones resourced because I can convince people to do it. So if you want to talk let me know in the break. And then that's the end of my time. So thank you very much, guys.